In this lecture, I'm going to be talking about dark matter, which is what you've been studying in your lab as well. And so some of this you should already be aware of by the time you watch this video. The reason that this whole question of dark matter comes up in the first place is when you think about the contradiction that we had at the end of the last lecture. We had a question of a contradiction between the observations of the density, which said that the density is much less than the critical density, and the observations of the geometry, which said we lived in a critical universe. So the question is, what did we get wrong? And so maybe we got a mass that is too low, or we got a density that's too low when we determined the density of the universe. And so we went into more detail about how do we get these masses, and people study the mass a little bit more carefully. And one thing you would study is the mass of a particular galaxy, and that's when we make these rotation curves. Those are these graphs that show how fast the object is moving on the y-axis as you go out from the center. So stuff in the center is not moving very much at all. As you go out, it gets faster and faster and faster. And the further out you go, this is what we actually observe, it gets faster, faster, faster. But if you just look at the amount of light there is and you figure mass based on the amount of light that's given off, you would expect this curve theoretically to look like this, based on the law of gravity. And obviously there's this huge difference between these two graphs. And in your lab, you're finding there's gigantic percent errors implied by the different masses that you determine from these. Because obviously, how fast you move is going to depend on the mass. It's going to depend on how much gravity there is. If the sun were much more massive than it is, we would be moving a lot faster because there's more gravity. We would be moving faster around the center of the sun. So your first thought, if you see, excuse me, stars in a galaxy that are moving faster than they should be, you would say, well, then there must be more matter there. There's more mass. Anything that's moving faster than we would expect, we would think there must be more mass. And so, but, you know, is that saying that there's mass that we can't see? That's sort of a weird result. What we have to conclude from this is one of two things. Maybe the way we're coming up with these masses is wrong. Maybe our law of gravity is wrong. Well, that's something we're not really happy to say. I mean, the law of gravity works. It's sort of the whole foundation of physics is the law of gravity. It works in every other circumstance. Why shouldn't it work for galaxies? Alternatively, we must be missing mass, and missing a lot of mass, like 75% of the mass. And the stuff that we're missing can't give off any kind of electromagnetic radiation. We've looked in X-rays and gamma rays and microwaves and infrared and all the other different parts of the electromagnetic spectrum. We're not seeing this mass. It's not visible in any kind of electromagnetic radiation. And so because it is not visible, we call it dark matter. And you can't see it in radio waves. You can't see it with any kind of radiation whatsoever. When we say it's dark, it's really dark. The only way we can detect it is by its effects on gravity. And this seems very disturbing, that there is so much of the mass that we can't see and we don't know what it is, because all of the matter that we're familiar with gives off light sooner or later. So that would be a really, really bizarre thing. And we don't have any of this stuff on Earth as far as we know. Why can't we find it? Why can't the astronauts find it if they go out into space? Shouldn't they be able to maybe feel it if they're floating around out there and they don't report anything? So what is this stuff if it makes up that much mass of the galaxy, and why don't we have any in the middle of our solar system? It's very perplexing, and yet the only other alternative is that the law of gravity is wrong. And then you say, okay, maybe there's another way to get the mass, and there is. And this comes from galaxy clusters. Now, this is a picture from the Hubble Space Telescope, and it's going to show you what I'm talking about, and then I'll explain what you see. In this picture, all of these yellow things are galaxies, and this is a cluster of galaxies. All these galaxies are bound together with gravity. And then you see these blue things. And this is another galaxy, except it's multiple images of the same galaxy. You have lots of little images of this one galaxy. And where that galaxy is really located is actually back here. Why do we see this sort of ring of images of this blue galaxy in this cluster? This is something called a gravitational lens. And this is a diagram from your book if you want to look it up in your book. What happens is we have a cluster of galaxies, and here's Earth, and there's a galaxy that's behind the cluster. Now, obviously, this is totally not to scale, but it's there to show you the concept. So from our perspective, this galaxy shouldn't be visible. It should be hidden behind the cluster. But Einstein says that mass bends light. It bends space-time, and that means that light bends as well. And a galaxy cluster has a ridiculously huge amount of mass. So it bends the light around it a lot. And the light coming from this galaxy bends around the cluster like this. But our eyes don't believe that light gets bent. Our eyes think that light comes in straight lines. So if we see a light ray coming in like this, we think it came in a straight line from back here. This is kind of how we see images from lenses, like you learned in physics. So we get these images of the galaxy back here, just like you would get the images from a lens. And so if you look through a telescope, instead of seeing the galaxy back there, you see it off to the sides. Well, the amount of matter there is in this cluster is going to determine how much it gets bent, and that'll tell you how far off to the side the images are supposed to be. And if you look at it and you start adding up the mass of all the galaxies in the cluster and you say, how much bending should there be? The amount of bending that we see is too much. The galaxies are too far off to the side, those little images. They're farther to the side than we would expect them to be based on the amount of mass that we can see. There's another one, just in case you were wondering. There's another example. And so this means one of two things. Either Einstein's theory of gravity is wrong, or there's dark matter that we can't see that's causing this greater bending. Now, Einstein's theory of gravity being wrong is a real problem here. We can't say, we're using Einstein's theory of gravity to figure this out in the first place. The fact that this exists depends on Einstein's theory of gravity being right. We wouldn't see any bending at all if his theory was wrong. So it doesn't make sense to think that Einstein's theory of gravity is wrong. Plus, we have tested Einstein's theory of gravity in many, 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 many other ways, and over and over and over again, it turns out to be right. So how can we possibly say that this theory is wrong? Well, the alternative is to assume that there is a huge amount of matter there that we can't see, that we don't know what it is. That's very, very perplexing, and again, that's dark matter. There's other evidence as well that I don't have time to go into, but you can read about in your book. Over and over again, we come to these conclusions that either there must be dark matter out there, or some basic theory that we really, really think is true must be wrong. One of those two things. And those theories have been tested in every other circumstance, and every other time they turn out to be right. So why would they be wrong here? It doesn't make sense. So let's suppose you think that dark matter really does exist, even if we don't know what it is, even if we can't detect it directly. Let's suppose you think it exists. Does that resolve that contradiction that we had about the fate of the universe? Well, it turns out that even if you include dark matter, the density of the universe is only 25 or 30% of the critical density. So this does not resolve the contradiction. The density is still way too low to give you a flat geometry. So even if you include this dark matter, which is tough to believe in, although astronomers do believe in it, you still can't resolve that contradiction. The density of the universe is still too low. And by the way, if you don't include dark matter, the density of the universe is only something like 4% of the critical density. So this is a very, very distinct difference.